Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Our mission impossible is simply to convert some of that hate energy to love energy. As your screen indicates, like it or not, math really did take us from the Stone Age to the Space Age. Now let's get down to some serious math. In this video series, we're going to be dealing with exponents. Specifically, we're going to be discussing exponent laws and how you use the exponent laws when you have mathematical expressions that, of course, involve exponents. And exponent laws are put in place in order to simplify expressions that contain these exponents. So, let's begin. The first thing we'll discuss is the product-sum law for exponents. Product-sum law for exponents. First of all, a power is an expression of the form a to the power b. A is called the base. That's what you're counting. And b is called the exponent. And that's essentially a frequency count. A to the power b is really a short form. It stands for a dot a dot a dot a dot a, etc. until you get to the final a. It's essentially a product string containing BAs. So this is the short form, a to the power b. The long version of that short form is a product of a's, and the product will contain b of them, and that's why we call b a frequency count for the base a. And we'll clarify by considering some simple examples. 3 to the power 4 really means 3.3.3.3. So there are 4 3's in the product. So 4 is the frequency count, the base is 3, and we write 3 to the power 4. And of course, 3.3.3.3 is simply 81. We can use fractions. We can have a fractional base. In this case, the base is 1/2 and the exponent is 3. And again, this is short form for 1/2 dot 1/2 dot 1/2. And of course, we know how to multiply fractions together. You just multiply all the numerators together. 1.1.1 is 1 and 2.2.2 is 8. And 1/8 is in reduced form. And we let it go at that. We'll go on to the next slide. The first law we'll be dealing with is the product-sum law. It reads a to the power b dot a to the power c is a to the power b plus c. I abbreviate that as PSL. Now let's see what this is really saying. Notice the a and the a match, and we have a dot in between. So we have a common base here. Base a, but the exponents may be different. Over here, this says that a to the power b, it says that a has a frequency count of b. So there are BAs. And a to the power c means that the frequency count for a here is c. So the total frequency count must be b plus c. And that's why this exponent law works, because you can compress this expression and just sum the exponents. That's why we call it the product-sum law. Because a product of 2 powers with a common base essentially becomes the base, and the resultant power is just the sum of the two exponents. So we illustrate via a few examples here. 2 to the power 3 dot 2 to the power 3. The common base is 2, and we simply add the exponents. This 2 occurs twice, and this 2 occurs 3 times. So the total frequency must be 2 plus 3, which is 5. So again, the exponents are just frequency counts for the time being anyway. Situations get much more complicated when the exponents are not whole numbers. But for the time being, let's keep it simple. You get 2 to the power 2 plus 3, which is 2 to the power 5. And of course, 2 to the power 5 is just 32. You can do this on your calculator using the power button, or you can just Multiply 2 by itself 5 times to get 32 if you wish. Okay, and to confirm, notice 2 to the power 2 is 4, 2 to the power 3 is 8, and 4 times 8 is 32. So that's another way of doing it. Second example, 3 to the power 3 dot 3 to the power 2. The common base is 3, so we just add the exponents. It becomes 3 to the power 3 plus 2, which becomes 3 to the power 5. And of course, you can use the power button on your calculator to calculate 3 to the power 5 to get 243. Or again, you can do it manually if you wish. The product sum law also applies if you have a fractional base. For example, 2/3 to the power 2 dot 2/3 to the power 4. The common base is 2/3. Again, 2/3 occurs twice here, and it occurs 4 times there. The total frequency count must be 6. So we write 2/3 to the power 2 plus 4, which becomes 2/3 to the power 6. And voila, this is the compressed form of the original expression. And of course, 2 to the power 6 just becomes 2/3 multiplied by itself 6 times. And you can certainly use the calculator on this to give you 64 over 729. Okay, an important note. A to the power 0 is defined to be 1, and this is valid if and only if a is not equal to 0, because 0 to the power 0 mathematically is undefined. And we won't go through the details of why it's undefined, but be careful about that. 0 to the power 0 is undefined, but you can put any base you want over here except for 0, and a to the power 0 will be 1. For example, negative 2 to the power 0 is 1, and 3 to the power 0 is 1. And also, like 2/3 to the power 0 will also give you 1. As long as the base is not 0, you're good to go here. A little bit of notation. CB will stand for a common base in subsequent problems to come. So let's go on to the next slide. Let's look at the first question. It says evaluate using the product sum law. So over here we have a product string, and we notice that the common base over here is 2. So we can certainly use the product law. We have one cluster because they're all dots in between the terms, and the common base we recognize is 2. So we're certainly in a position to use the product sum law. So in the next step, we write 2 to the power 1 plus 3 plus 2. So the total frequency count is 6. And 2 to the power 6 is just 64. And you can verify that on your calculator if you wish. Let's look at Q2. Again, we're going to be using the product sum law. If we look at this question carefully, we identify 2 clusters this time. The separator is the plus sign. If we look at the first cluster, the common base is 2. Second cluster, the common base is also 2. And what we do is identify the common bases for each cluster. It's 2 and 2. And we use the product sum law for each cluster. Okay, you can't use the product sum law between clusters, only within a cluster. So within the first cluster, we get 2 to the power 2 plus 1. Plus, in the second cluster, we get 2 to the power 3 plus 0. And then simplify each cluster. We get 2 to the power 3 here, 2 to the power 3 here. And of course, 2 to the power 3 is 8. And 2 to the power 3 is 8. And 8 plus 8 is 16. So all pretty simple so far. Let's have a look at Q5. Again, we're using the product sum law. And if we look at this expression over here, we identify 3 clusters this time. The separators between the clusters are that minus sign and the plus sign. If we examine the first cluster, the common base is 2. Second cluster, the common base is 3. Third cluster, the common base is 5. So again, we identify 3 clusters, and the common bases are 2, 3, and 5 respectively for each cluster. Again, we can use the product sum law. The first cluster becomes 2 to the power 2 plus 1. Minus sign, drop it down. The second cluster becomes 3 to the power 3 plus 1 plus 0. Then we hit a plus sign, drop it down. The third cluster is 5 to the power 2 plus 2. And again, you simplify the exponents for each cluster. Over here, we get 2 to the power 3. Drop the minus sign down, we get 3 to the power 4. Drop the plus sign down, we get 5 to the power 4. And now we can use the power button on the calculator, or, if you're adventurous, just do it manually. But that's really not necessary in this day and age. You're certainly allowed to use the power button. We get 2 to the power 3 is 8. Bring the minus sign down. 3 to the power 4 is 81. Bring the plus sign down. 5 to the power 4 is 625. At the end, we've got an integer string. So we just add up the good guys to get 633. And we add up the bad guys to get minus 81. And again, the good guys win. And you do plus to indicate that the good guys win. And then you do large minus small. And when you work that out, you can drop the plus sign and get 552. Let's go on to Q6. This is just a little bit different. When we look carefully over here, we notice a separator here and a separator there. So we identified 3 clusters. But now the first cluster has 2 different bases, so we can't apply the product sum law. Same thing with the second cluster, 2 different bases. And the third cluster, 2 different bases. So the product sum law cannot be used. Okay, so we go into the next step. Can't do anything, so just drop everything down, nothing to do. And we evaluate each power. We get 2 to the power 2 is 4, 3 to the power 1 is 3. Drop the minus sign down, 3 to the power 2 is 9, 2 to the power 1 is 2. And drop the plus sign down, 3 to the power 2 is 9, and 5 is a drop down. And of course, all you have to do now is compute each product over here. We have 4.3, which is 12. Bring the minus sign down. 9.2 is 18. 9.5 is 45. We have a simple integer string at the end. We have some good guys and some bad guys. Specifically, we have 57 good guys and we have 18 bad guys. The good guys win, so you put a plus sign out front, and then you do large minus small. And of course, the final answer is 39. We could drop the plus. And let's go on to the next slide. Again, it says evaluate using the product sum law. So we have 2 to the power 2, dot 3 to the power 1, dot 2 to the power 1, dot 3 to the power 2. Notice there are no plus or minus separators over here. So this constitutes one cluster. It's a single cluster. But if you look within this cluster, the common bases are 2 and 3. And we can always apply the product sum law within a cluster. And that's exactly what we're going to do. We consider each base in turn. I usually like to start off with the smallest base and proceed to the larger base. So we start off with base 2. You disregard all the base 3 terms. So when you look over here, you open up base 2 and you collect 2 plus 1. There it is right there. Then you put a dot. Now you collect for base 3. That's essentially what we're doing, is collecting exponents for each base. When you collect, you get a 1 plus 2. And in the next step, 2 to the power 2 plus 1 is just 2 to the power 3. And this becomes 3 to the power 3. And again, you cannot join these up using the product sum law. So we must perform an evaluation at this point. We get 2 to the power 3 is 8, 3 to the power 3 is 27. And of course, this product is 216. Let's go on to Q10. If we look for separators over here, like of the plus minus form, there are no separators. So this constitutes, again, a single cluster. So we identify the common bases over here as 2, 3, and 5. And we can certainly apply the product sum law whenever appropriate, because we can always apply the product sum law within a single cluster. Not between clusters, but within a single cluster, you can always do it. Again, we start off with base 2, and we collect. We get a 3 plus 1, and we drop it in the exponent. Then we'll deal with base 3, and we get a 1 plus 2, drop it in the exponent. And then we deal with base 5, put the base down, and collect the exponents for base 5, you get a 2 plus 0. Again, we're using the product sum law at this point. You cannot use the product sum law between bases that are different, okay? So make sure you don't attempt to do that because that's completely invalid. Again, we simplify further. We get 2 to the power 4 here, drop it in there. We get 3 to the power 3, drop it in there. 5 to the power 2, drop it in there. Now we evaluate each power in turn. 2 to the power 4 is 16, 3 to the power 3 is 27, and 5 to the power 2 is 25. At the end, we have a product string. Just perform the product, and you get 10800 as your final answer. And let's proceed on to the next slide. And I think we're going to call it quits for this video. Stay tuned for the next video. Thanks to all for viewing this video. Stay tuned for many more to come. If you liked the video, please give us a like and subscribe to our channel. If not, tell us how to improve it. Over and out for MATLAB Tutorials in Toronto.